Is the screen visible?
Yes, ma'am.
ठीक है, तो let us start. So in today's class, we are going to start with the new topic. These are the FETs or field effect transistors. So what are FETs? Basically, FETs are another type of transistor, as it's already evident from the name. And since it's a transistor, it is also a three-terminal device. And this three-terminal device, this uses electric field to control the current flowing in the device. So this is how we are going to define an FET. That FET is a transistor, a three-terminal device, wherein electric field will be used to control the current which is flowing in the device. So these three terminals, in case of FETs, they are called as gate, also denoted as G. Other terminal is the drain, denoted as D. And the third is the source. This is denoted as S. So if you compare this with respect to BJT, then a gate is analogous to the base, the drain is analogous to the collector, and the source is analogous to an emitter. So if I have to talk about the very basic working of the FET without going into much detail, then I can explain it with the help of a very simple diagram. So here you have the gate terminal, and here you have the drain terminal, and here you have the source terminal. So some figure of this sort you are going to see when we are discussing the FETs. And the current in this case flows from drain to the source. We call this as the drain current, and this is also the output current of the FET. And the input voltage is applied across the gate and the source. We call this as VGS. So when I apply VGS between the gate and the source terminal, what happens? It creates an electric field inside the device. And this electric field then controls how much the current is going to flow. So that means with the help of input voltage VGS, I am controlling the output current ID. This is my input voltage and this is my output current. So this is the very basic working. And from here, it's also intuitive why we get the name field effect. So here field stands for the electric field. This is called field effect because the output current varies under the effect of electric field that is produced by the input voltage. Also, you see over here, because the input voltage is controlling the output current, the FETs are also known as voltage controlled current source. So at the output, you get a current which is controlled by the input voltage. That's why these are also known as the voltage controlled current source. So this is about the introduction of FET. So basically it is a transistor. It has three terminals and the output current is controlled by the input voltage. This is the summary. Now what we are going to do is, just for the clarity of understanding, we are going to see the differences between the BJT and the FET. So in case of BJT, if if you recall the output characteristics, say for example, I'm talking about the common emitter configuration. So in the common emitter configuration, the output characteristic was between the output current IC and the output voltage VCE. And we also saw that this output current is actually controlled by different values of base current, which in this case was the input current. So that means the output current in case of BJT was controlled by the input current. That is why we say that the BJTs are current controlled current sources. These are current controlled current sources. Whereas for the case of FET, we just saw that these are actually voltage controlled current sources. So this is the first difference. The second difference is, if you remember, in case of BJT, we said that these are bipolar devices. So what do you mean by bipolar devices? That means the current in the case of BJT flows because of the presence of majority carriers, also because of the presence of minority carriers. There are two types of current in the BJTs, whereas in case of FET, this is a unipolar device. So since it's a unipolar device, we are going to have only one type of current which will flow through the effect of majority carriers. So that means this is going to make our life simpler, because now we have to deal only with one type of current and not two types of currents. Then the third point, which is a very important point, is that in case of FET, the input impedance is very high. So the input impedance is very high. That means this is generally on the order of, it starts from 1 mega ohm and it could be on the order of hundreds of mega ohms. Whereas in case of BJT, this is not so high. This is only on the order of kilo ohms. So why do we have this very high input impedance in case of FET? So this is actually attributed to the way how these FETs are fabricated. So what actually happens is there's an isolation layer. There's an isolation layer that exists between the gate and the channel. And the purpose of this isolation layer is actually to stop any minority carriers from flowing into the channel. I will not go into the detail because this is not the scope of this course, and anyways those who belong to this specialization will read this in much detail in the coming semester. So for now we can only keep in mind that the input impedance for FET is very high, and this is because of the way how these FETs are fabricated. Basically this is to inhibit the flow of current because of the minority carriers. And this is a very, very important property because this is going to be used again and again in solving the question. So because input impedance is very high, the input current is actually zero. So input current is the current which appears at the gate. So whenever you are going to solve the questions for FET, you will always see that the gate current is zero, irrespective of whatever voltage you have applied in the input or whatever voltage you are obtaining at the output. So that's the third important point. Then, okay. Then in the case of BJT, so while we say that FET has very high input impedance, in case of BJTs, it is actually more sensitive to the change in applied signal. So the point here is, in case of FET, input impedance is high, whereas for the case of BJT, the sensitivity is high. So what do I mean by the sensitivity in this case? This means that the change in output current, that is delta IC, the change in output current, or let me write this as change in output current, is actually high in case of BJT as compared to FET for same change in input voltage. So that indirectly means that the current gain which is obtained through the BJT will be high as that obtained through FET. Why? Because the sensitivity over here is high. If the sensitivity is high, that means even for small change in output voltage, even for small change in input voltage, the change in output voltage is going to be very large. So now if the gain of BJT is very high, then why do we need an FET? Because ultimately BJTs and FETs primary application is the amplifier, where it matters which transistor is giving how much gain. So obviously BJT gives more gain, then this should be the preferred one, but this is actually not true. Why? Because the FETs are actually more stable with respect to the changes in temperature. More stable with respect to changes in temperature. And also one of the very important point is the size of FET. So generally these FETs are more compact compared to the BJT. Therefore, very important use of FETs is in the fabrication of integrated circuits. And as you all know that integrated circuits are now used for, almost all the electronic devices, be it a very basic electronic device to a very complicated, maybe a laptop or very high-end machines or whatever. So that is another advantage of FETs over BJTs. So this kind of summarizes the differences. Three differences are more important, I would say, is that you need to understand that FET is voltage controlled, also it's unipolar, and its input impedance is very, very high. So now given the differences, let us see the types of FETs. So in FETs, we have two main types. The first type is the junction field effect transistor. This is known as JFET. And the second type is insulated gate field effect transistor, that is IGFET. Then this JFET can be further distinguished based on if it is N channel or if it is P channel. Whereas IGFET, they have some diversification. So the most important type of IGFET which is used is known as MOSFET. MOSFET stands for metal oxide semiconductor field effect transistor. And one more category also exists which we call as MESFETs. So this is simply metal semiconductor field effect transistor. Then MOSFETs also have two types. This could be depletion type MOSFET or enhancement type MOSFET. This we are going to do when we will study the MOSFET. Right now I'm just taking the names so that you are aware. And then this depletion type and enhancement type MOSFETs can be further N channel or P channel. So this is my broad classification. Basically two types, junction field effect and insulated gate field effect. Then junction field effect could be N channel, P channel. IGFET we will talk only about MOSFET. So you can keep in mind that MOSFET is again of two types, depletion type or enhancement type, and then again each of them can be differentiated based on if it is an N channel or if it's a P channel. Okay, so now we will start with the construction of JFET. So here basically we are talking about the N channel JFET, but the concepts that we discussed, they also hold for P channel, only there will be sometimes change in the direction of current. So once we are done with the N channel, then maybe I'll briefly discuss the P channel so that you have an idea of what to change when in the question you have a P channel instead of N channel. For now, let us concentrate on the construction of the N channel. So here you see, this is the basic diagram which shows the construction of an FET, and here you see that the major part of this structure is an N-type material And this N-type material forms a channel. So this passage which you are seeing over here, this is known as the channel. And this N-type channel is actually embedded between two layers of P-type material. So there will be a channel. This will be N channel because this is N channel. So this is N type. And then this will be interleaved between the two P-type material. Then the top of the channel through an ohmic contact, as you see over here, through an ohmic contact, this is connected to the drain terminal, and the bottom of the channel through an ohmic contact is connected to the source of the terminal, to the source terminal. So here, as of now, because externally no voltages have been applied, so and the structure is also symmetrical, so any terminal could be the drain or the source. But once you apply the external voltages, then you need to keep in mind that source is the terminal from where majority carriers are going to enter the junction. That terminal from where majority carriers should enter the junction is the source. And likewise, the drain is that terminal from where the majority carriers exit the junction. Oh, sorry, exit the channel. This is also channel. So that is how you differentiate between the source and the drain. So it is not like which is at the top is the drain and which is at the bottom is the source. This is not the distinction. The distinction is that the terminal from where majority carriers are entering into the channel is the source, and the terminal from where the majority carriers are exiting the channel is the drain. Then these two P-type materials, they are internally connected to each other, and then through the ohmic contact, it is connected to the third terminal, which is the gate. So if you see the construction, you will see that there are two junctions. One is between the first P layer and the N channel, and second is between the second P layer and the N channel. And in between these junctions, there is also a depletion layer which actually exists between any PN junction. So this is my basic structure. There will be a channel, and then there will be P-type regions which will be connected to the gate, and the channel will be connected to the drain and the source. This is the basic construction. Then here you have the circuit symbol of the JFET. This looks like this. So again, I need you to observe this arrow over here. If this arrow is pointing inwards, then this suggests that this is the symbol for an N-channel JFET. If this is outward, for example, like we will see later on, if this is how the direction is marked, then this signifies that this is a P channel. This we will see later. For now, you need to keep in mind that for an N channel, the arrow on the gate terminal is inwards. Also, the direction of the drain current is inside. Why this is inside? Because we know that in case of N channels, the majority carriers are actually electrons. And source is the terminal from where the majority carriers will enter into the channel. So electrons are entering over here and they will leave from here. So the flow of electrons is in this direction. Therefore, the flow of conventional current is in the opposite direction, that is from drain towards the source. So that is how I mark the direction of drain current from drain to the source. And across the drain and the source terminal, I mark the voltage VDS. This will also be our output voltage. And likewise, across the gate and the source, we have voltage VGS, which will denote our input voltage. So variation in input voltage is going to control the output current ID and also the output voltage VDS. Okay, any doubt as of now? No? Okay. So if there's no doubt, then let us see the working. So here we have connected the N channel JFET in this way. So the drain terminal and the source terminal have been connected to positive voltage VDD, where obviously VDD is same as VDS because this is just connected in parallel. And then across the gate and the source, we have connected VGG. So just see over here, observe over here that VGG is negative. VGG is negative, whereas VDS was positive. So why this VGG is negative over here? Because first of all, we said that the input impedance of JFET is very high. So if the input impedance is very high, even if you apply the positive voltage, it will not make any difference to the input current. क्योंकि अगर the input impedance is on the order of mega ohms, then इसके across current flow करवाने के लिए you have to apply voltage which should be on the order of thousands, and applying such high voltage to electronic devices is not possible. तो जिस रेंज ऑफ वोल्टेज में हम इलेक्ट्रॉनिक डिवाइसेस के साथ काम करते हैं, लाइक 10 वोल्ट्स और मे बी 5 वोल्ट्स, 3 वोल्ट्स, तो अगर इतना पॉजिटिव वोल्टेज लगा भी देंगे इनपुट के अक्रॉस, so it will not make any difference to the flow of input current. That's why applying positive voltage at the input is actually meaningless in case of JFET. But if I apply negative voltage, then you will see that this actually adds to the reverse bias inside the gate source junction, and because of this we can have some variation in the output current. So this we are going to see in the slides to come. So for now you can only keep in mind that across the input, that is VGS, either we will keep VGS as 0 or we will keep VGS as some negative value but not positive voltage. And VDS, this will be positive. So now let us see the first condition. In the first condition, we say that we have not applied any voltage. So if I have not applied any voltage, that means this connection is also open and this connection is also open. So your resultant JFET is going to look like this. The gate is internally shorted, which is shown by this line over here, and since there are no external voltage, so we will simply have two PN junctions under no bias condition. Abhi kuch nahi ho raha hai. You can say that this is state 0 when nothing is happening, no voltage is applied. So simply you will have two PN junction, there will be depletion layer between the PN junction, and observe that in this case the depletion layer width is symmetrical in both the cases. I mean symmetrical for this junction also, symmetrical for this junction also. As well as if you take the horizontal symmetry, then on the top also this is symmetrical, on the bottom also it's symmetrical. So both ways, vertically also it's symmetrical and horizontally it's also symmetrical. This is the base case where you have not applied any voltages. Now what we do is, the second condition that we analyze is VGS is 0 and at the same time we apply some positive voltage across the drain and the source. So here you see that between the drain and the source terminal we have applied some positive voltage which is denoted through this battery, and the gate and the source terminal, they are connected through a wire, or in a sense they are shorted, which is realizing the condition of VGS is equal to 0. So now what happens when the gate and the source, they are shorted, then the depletion region which is towards the bottom of the channel, this depletion region, this is actually similar to what we have observed in the case of no bias. ठीक है, यहाँ पे भी ऐसे ही था, लोअर रीजन में देयर वाज सिमेट्री, यहाँ पे भी ऐसे ही होता है, बिकॉज द गेट एंड द सोर्स टर्मिनल्स आर शॉर्टेड, सो दिस शेप डज नॉट चेंज. The upper shape changes, and this we are going to discuss in a while. So before that, what we do is we increase the value of VDS starting from 0. So if VDS is increased, then what happens? The electrons from the source terminal are drawn towards the gate drain terminal, and in turn a current ID flows from drain to the source. ठीक है, सो फर्स्ट थिंग इज VGS को 0 किया, डिप्लीशन लेयर अभी चेंज नहीं हुआ है, एटलीस्ट इन द लोअर पार्ट ऑफ द चैनल, एंड देन ऑन इंक्रीजिंग VDS द करंट ID starts flowing. Now, when the current ID starts flowing, what happens is we actually say that this N channel, जो channel है, this actually has a uniform resistance. And to understand this change in shape over here, what we do is we model this uniform resistance by series of resistances consisting of different levels. So the idea is, because we say that the resistance of this N channel is uniform, so let us say that at different levels, this will be given by different resistances. So here each resistance is having same value. मान लो हर एक resistance की value 1 ohm है. And the voltage which is applied over here is 2 volts. If 2 volt voltage is applied, how much voltage drop will happen across this resistance? This will be 1 because its value is 1. Say for example, if it was 1 divided by the total resistance. Total resistance कितना लगाया हमने? 1, 2, 3, 4. So this will be 4 and multiplied by 2. So that means 0.5 volts will be the voltage drop across this first resistance. So if out of 2 volts 0.5 volts drops over here, तो यहाँ पे इस point पे कितना voltage बचा? That is equal to 2 minus 0.5 equal to 1.5 volts. Similarly, when you move from this point to this point, another 0.5 volt drops and the remaining voltage is 1 volt. Then from here to this point, another 0.5 voltage drops and the voltage remaining is 0.5, and then eventually it comes out to be 0. So what is the effect of this different voltages over here? So first thing that you need to understand is that these voltage drops are actually positive because you have applied positive voltage over here. But the channel is N-type. So when you have positive voltages inside the N-type channel, this reverse biases the junction across the length of the channel. ठीक है, तो इन voltages की वजह से this entire junction, both the junctions, they are becoming reverse biased. And also keep in mind that this reverse bias voltage is high towards the top, whereas it is low towards the bottom. And we already know that if the reverse bias voltage is high, the depletion region is going to expand. So this is the reason why we have this kind of shape. So towards the top of the channel where the reverse biasing is more, the depletion region is wider compared to the depletion region at the bottom of the N channel. Okay, so this is about the shape of this depletion region. Then another point that we need to observe over here is that the gate current is shown to be 0. So of course this is 0 because VGS is 0 right now. And we also know that because of very high input impedance, this has to remain 0. And by one more fact, we can support this argument, and that fact is that the channel is actually throughout reverse biased for the entire length of the channel. That's why there is no scope of flow of any current from this gate terminal inside the channel. So that's why we say that the input current or gate current is equal to 0. And this is a very important property of the FETs. So now let us see how does the current change as you increase the value of VDS. So एक चीज तो पता चल गई कि VDS जब हम 0 से increase करेंगे तो drain current is going to flow through this. And when the drain current flows, the depletion region shape changes from uniform, as in over here, to somewhat distorted form, which is shown over here. तो ये इस slide से पता चला. Now let us see how ID varies by change in VDS. So this we are going to see through this plot. So observe that this plot is the plot between ID and VDS, where my ID is the output current and VDS is also the output voltage. So that's why this plot is known as the output characteristic of the JFET. Or sometimes it's also known as the drain characteristics. So what happens in this region? I want you to concentrate over here. In this region, when VDS is increasing from 0 up to some small value. In this region, you see that the slope is almost constant. The slope is almost constant. So what is the slope of the curve over here? The slope will be delta ID divided by delta VDS. So this is going to be, this is current divided by voltage. So that will be the conductance of this JFET. So if the conductance is fixed, that means the resistance is also fixed. Also understand that because this is the output current and this is the output voltage, so this resistance what we are talking over here is actually the output resistance or output impedance of FET. We are not talking about the input impedance. That we know it will already be on the order of mega ohms because of the type of fabrication of FET. So here we are talking about the output resistance. So in this region, when VDS is increasing from 0, the conductance and hence the resistance of the FET remains almost constant. This is the first region. Then I want you to observe this part. So here what happens, as you increase VDS further and it approaches this voltage which is shown as VP over here. VP stands for pinch off voltage. So as VDS is approaching VP, तो क्या हो रहा है? The slope is reducing. So initially, if I say that for some X change in VDS, अगर change in if for X change in VDS there was Y change in ID, then now in this region what will happen? For the same change X, the change in the current will be much less. This will be Y minus some Y dash. That means the slope in this region is reducing. You can also see this is apparent. यहाँ पे ज़्यादा steep है curve, यहाँ पे कम steep है curve. तो slope is reducing का मतलब क्या हुआ? Slope reducing का मतलब the conductance is reducing. And if the conductance is reducing, that means the resistance in this region is increasing. So that means as VDS approaches the pinch of voltage, the resistance increases. And eventually, when VDS is actually equal to VP, that time the curve becomes entirely flat. That means in this region, curve becomes flat. That means the slope is 0. That means conductance is 0, or you can say that the resistance almost becomes infinity. So this region where the slope is becoming 0 is denoted by IDSS, or the saturation current, maximum saturation current. This is known as maximum saturation current or IDSS. So now let us see why this is happening. Okay, initially तो समझ में आया why this is increasing in a steep manner, because the resistance across the channel was uniform, and if the resistance is uniform, you increase the value of voltage, then accordingly the current increases. That is the reason for this curve being linear over here. अब क्या होता है कि जब VDS is approaching this VP, what happens? The depletion. Actually, if you are increasing VDS, then you need to remember that you are increasing the reverse bias across these junctions. And increase in reverse bias is actually going to widen the depletion region. So as I am increasing the value of VDS, in fact, the reverse bias voltage in the channel is increasing, which is causing the depletion regions to widen and widen. And when VDS exactly becomes equal to VP, then at this time, it appears that the two depletion regions are almost touching each other. Just pay attention, so I am emphasizing on the word almost, because it's not that they have completely touched each other. So when VDS is equal to VP, it appears that the two depletion regions in the top portion of the channel are almost touching each other. And this condition is known as the pinch-off condition. And correspondingly, this voltage VP is known as the pinch-off voltage. So pinch-off is actually kind of a misnomer. Pinch-off का मतलब ये नहीं है कि ये दोनों ने एकदम touch कर लिया और current ID pinch-off हो गया and it becomes 0. This is not the case. what actually happens is, because I'm saying they almost touch each other, that means there is still a very narrow channel. In reality, a very narrow channel still exists between these two extended depletion layers. तो क्या होता है कि जब इलेक्ट्रॉन्स पास करते हैं यहाँ से, तो इनिशियली दे हैड लार्ज एरिया, सो दे वर स्प्रेड आउट. But once they have to pass through this very narrow strip, then lot of electrons, they are constricted to a very small region. So in this case, the current density becomes very high. So the current will not going to increase further as it was increasing in this region, but rather initially, because of increase in resistance, the current increase reduces, and then finally jitna value usne attain kar liya tha at the time of pinch off, it is going to maintain that value for rest of the drain characteristics. So here again I'm repeating, in this region we say that the resistance is infinity, and here we are talking about the output resistance. So output resistance is infinite, but that does not mean that the output current is also zero. This is a thing that you always have to keep in mind. Otherwise you may think कि output resistance infinite है तो output current तो zero होना चाहिए. It is not zero, and why it is not zero? Because actually they do not touch each other completely. There is always a small gap through which a very high density current is going to pass through. तो Vp आने तक जितना current attain हो जाता है, उतना current is maintained for rest of the values of VDS. And of course, this is the desirable region of operation. इसके आगे अगर आप VDS को increase करोगे, then there would be a tendency that the drain current increases abruptly, and this is also known as the breakdown region. So we do not want our transistor to go into the breakdown region. So the safe operation limit is up to this point. These values are generally specified in the specification sheet. Is this clear? Any doubt? So here IDSS जो है, this is defined as the maximum drain current. And maximum drain current होने के क्या characteristics हैं? VGS should be equal to 0 and VDS should be greater than mod of VP. So here, because it's an N channel के लिए VP is a negative value. So here in the plot, this should actually be mod VP. So VDS has to be greater than mod VP and VGS should be equal to 0. Then the corresponding saturation current is known as IDSS. So for all this discussion that we have done as of now, we saw that the value of VGS was equal to 0 volts. अब हम क्या करते हैं? अब हम VGS की वैल्यू को चेंज करके देखते हैं. So earlier we know that we said कि VGS will not be positive. So let us vary VGS towards the negative side. So initially it was 0. Let me now say that I have applied -1 volts. So what happens when you apply a negative voltage? Then you are going to attain the saturation at low levels of VDS. So if you observe over here in this plot, VGS is equal to 0 is the plot which is having the highest saturation current, that is IDSS. Now when I apply negative voltage over here and make VGS is equal to -1, then two things are happening. First of all, drain current की value reduce हो जा रही है, and second is pinch off voltage is also reducing. So earlier pinch off voltage was over here. This point corresponds to this point. But यहाँ पे क्या हो रहा है? The pinch off voltage will move slightly towards this point. So now the new pinch off voltage is somewhere over here. So why this is happening? So reduction in the drain current is quite obvious, because in the previous slide we saw that already the channel is reverse biased. Already the channel is reverse biased because of positive values of VDS. Now, if you add to this reverse bias by reverse biasing further this junction, then it actually increases the amount of reverse bias in the channel. And increase in the reverse bias causes the output current to reduce. So that is one very straightforward reason why on reducing VGS to a negative value, the drain current reduces. And then what about the pinch off voltage? So if you see over here, this curve which is shown by a dashed line is the locus of pinch off values. Locus means the path. Path means how the pinch off voltage is going to change by changing the value of VGS. And this path has the equation VDS is equal to VGS minus VP. So just see for the first curve. पहले वाले कर्व पे देखो, अगर मैं कहती हूं कि Vp is equal to -3 volts for this FET, then what will happen? पहले वाले कर्व के लिए क्या होगा? What will be the value of VDS? Because VGS is equal to 0. So this will be minus of -3, that is equal to +3. So that means at VDS is equal to +3, you will have the saturation current. Now, if I say I have reduced the value of VGS from 0 to -1, then what will happen to VDS in this case? This will be -1 minus of -3. This will be -1 plus 3 equal to 2 volts. That means now the saturation of the drain current is going to happen at 2 volts. So we have the same characteristics, but now this is happening for low values of VDS. And as you keep on increasing the VGS, the drain current and hence the value of pinch off current is going to further reduce until at this point. At this point, what happens? If I say that VGS becomes exactly equal to minus VP. तो उस केस में क्या होगा? What will be VDS? This will be equal to minus VP minus of minus VP. This will be equal to 0. So that means when VGS is equal to VP, at that time your output voltage will become 0. And if output voltage becomes 0, the drain current will also become 0. So it is almost this horizontal axis. So although majority carriers की वजह से current 0 है, but there will be still small reverse saturation current which is on the order of nanoamperes, which we usually ignore. So that's why towards the horizontal axis, this region is known as the cutoff region of the transistor. And in this region, we can assume that the device is practically cut off. And the condition for this is VGS should be equal to minus VP. And the output voltage will be 0, the output current will also be 0. Similarly, if you see the region towards the right hand side of this dotted curve, so this dotted curve which was the locus is given by this equation VDS is equal to VGS minus VP. If you move towards the right of this curve, then this is known as the active region or the saturation region. Sometimes it is also called the pinch off region of the transistor. And the equation for this is that VDS will be greater than VGS minus VP. This is the condition for the transistor to be working in the active region or the pinch off region or the saturation region. And you know, when this condition is satisfied, when the transistor is working in the active region, you will have constant output current for a given value of VGS. Also observe that these saturation values, they are not called IDSS. IDSS केवल top वाली value होगी. बाकी other currents are just the saturation current, but the maximum saturation current is what we call IDSS. So this is the active region. And the third region is this region that is towards the left of this locus. And the condition to this is VDS should be less than VGS minus VP. and we call this region as the ohmic region. So in the ohmic region, the resistance of the transistor is going to vary. Therefore, in this region, it is sometimes also used as a variable resistor. Whereas in the active region, the transistor is used for the purpose of amplification. Amplifier की तरह use कर सकते हैं, oscillator की तरह use कर सकते हैं. So there are many applications for the transistor working in the active region, but in the ohmic region, basic application is that it could work as a variable resistor. So now we have seen that based on the working of the transistor, it could be characterized into three regions. Either it is the cutoff region or the ohmic region or the active region. Okay? Sometimes this active region is also known as linear region. So don't get confused that linear region is the ohmic region. Linear region इसलिए कहते हैं क्योंकि यहाँ पे it can be used for the purpose of linear amplification of the signal. So linear region still means the active region or the saturation region. The terminologies are a bit different. So now I'll just write down the equations because derivations of the equations are not what I'm going to discuss. So in case of the transistor working in the ohmic region, the equation of drain current ID is given as IDSS into 2 1 minus VGS by VP multiplied by VDS by minus VP minus VDS by VP whole square. So this is the equation for the drain current when the transistor is working in the ohmic region. So generally, if VDS value is very small, then you can ignore this VDS by VP whole square term which is appearing over here. So in that case, your ID expression will be a bit simplified. So this will be IDSS 2 times of 1 minus VGS by VP into VDS by minus VP. This will be my equation, and in more standard form which you will see in the textbook, it is slightly rearranged to look like this. This will be 2 IDSS divided by minus VP into 1 minus VGS by VP into VDS. So this is the equation of my drain current when the transistor is working in the ohmic region. And correspondingly, if I want to find out the resistance, that is the output resistance, RDS. So this will be VDS divided by ID. So if you use this expression over here, if you substitute this, you are going to get the expression for output resistance as VP square divided by 2 times of IDSS into VGS minus VP. This is the resistance that my FET is going to offer when working in the ohmic region. Then if the transistor is working in the active region, then in that case, the drain current is given by ID is equal to IDSS into 1 minus VGS by VP whole square. This is the equation of the transistor working in the active region. So from here, if you actually want to see a plot between ID versus VGS. So remember, ID was what? This was output current, and VGS is what? This is input voltage. So from here, if I plot a graph between ID and VGS, it is going to look like this. And this is known as the transfer characteristic of the FET. ट्रांसफर क्यों कहते हैं इसको? बिकॉज वाई एक्सिस पे जो क्वांटिटी है दिस इज द आउटपुट क्वांटिटी और एक्स एक्सिस पे जो क्वांटिटी है दिस इज द इनपुट क्वांटिटी. दैट्स व्हाई दिस कैरेक्टरिस्टिक इज कॉल्ड द ट्रांसफर कैरेक्टरिस्टिक. So this we have already seen that when VGS is equal to minus VP, at that time the drain current is 0. And if you go on increasing the value of VGS towards 0, so at 0 this will be maximum value which is IDSS. And in between this is going to increase, and the increase is governed by this equation which is shown over here. ठीक है? And one more last thing, छोटी सी condition है. So at the boundary of ohmic and active region, we know that VDS will be equal to VGS minus VP. So if this is the boundary at which I am talking about. तो ये जो dashed curve है इसकी बात कर रही हूँ. ये dashed curve is actually the boundary between the ohmic region and the active region. So the equation of this dashed boundary is actually VDS is equal to VGS minus VP. So correspondingly, if I want to see what will be the drain current at the boundary, then this we know that this is given by IDSS into 1 minus VGS by VP whole square. So if you substitute this, this becomes IDSS into VP minus VGS divided by VP ka whole square. So this will be ID is equal to IDSS into, this is minus of VDS from this equation, and if you square, this will be VDS square divided by VP square. So this is the drain current exactly at the boundary of the ohmic region and the active region. So this is in reference to the output characteristic and not the transfer characteristics. So with this, we have pretty much all the concepts that will be required for solving the questions. I'll stop here for today. In the next class, we will see a few questions wherein JFET are used in the circuits. And then with brief discussion on P channel, we will move to the MOSFETs. So any doubt if you have, you can ask now.